really quantify this effect. Remember, in a capacitor circuit, and I want to use that circuit as our lead-in today. If we have a resistor and a capacitor in a circuit, we define capacitance based on how much charge a capacitor would hold under the conditions of having a voltage applied. So we said that the capacitance was equal to the charge per unit volt, and defined capacitance in that way. From here, we would say that, in a Kirchhoff's loop relationship, the voltage drop across the resistor and the voltage drop across the capacitor would be related to this ratio. So we would say that the voltage drop across the capacitor is equal to Q over C. And that's how we would plug that into our relationships that had capacitors in them. For Kirchhoff's law relationship here, we say V minus VR minus VC equals 0, and we would have done something like V minus IR minus Q over C equals 0. Kirchhoff's law and definition of capacitance. Does that jog your memory from a while ago? So let's apply that in this arrangement based on what we talked about in class. And if you weren't here, well, I'm sure I recorded it, but I don't know if I posted it. An inductor has a symbol that looks kind of like that. We draw it to be as if it were a mini solenoid. I tend to try and be careful when drawing this symbol because if you start rushing it, it tends to look like either a bulb or a resistor if you're really bad. So if we have an applied EMF, we use a capital L as the symbol for inductance. Now, just kind of a reminder of how this worked on Friday. The idea is that an EMF is produced whenever there's a change in the flux in your inductor. So inductance is about when something changes. If we have no current in the system and I go to close this switch, well, currently inside the inductor, before the switch is closed, there's no current in the wires that are being used to create the inductance. So right now, current equals 0. That also means that there's no magnetic field inside the inductor. So when I first go to close this switch, well, because there's no magnetic field, the moment the switch is closed, then the current's going to go from 0 and attempt to go to some other value. Well, because there's no magnetic field there currently, there's going to be a back EMF in this direction, this way, across the inductor, that's going to attempt to prevent the establishment of this current by trying to prevent the establishment of the magnetic field. And if we do a quick run through with our right-hand rule, the current's trying to go this way through those wires, correct? So if we do a bit of right-hand rule, that means the current is trying to go this way, right, through that portion of the wire. I use my little curl rule, and that suggests that a magnetic field in this direction is trying to be established. That's what it's trying to establish, a magnetic field in that direction. Well, this change in flux produces an EMF. And the EMF that's trying to be produced is one that's going to try and prevent the establishment of that magnetic field. which means there's going to be a induced EMF and current to oppose the change. And that's what's happening here. Now, I'm going to leave the magnetic field lines out of the drawing for just a minute to kind of advance this. Let's say that after a long time, we get a fully established current in the system. Because although it may prevent it or try to prevent it, eventually the applied EMF is going to win out, and we will get a fully established current in the circuit. The amount of current in the circuit would be based on Ohm's law at this point and the total resistance of the circuit. And at that point, we would have a fully established magnetic field through the center. This means eventually we reach a steady state condition. And in the steady state condition, we have a constant current passing through our circuit. This is expressly different than a capacitor circuit. In the steady state condition of a capacitor circuit, there's no current when we reach the steady state condition. But in this circuit, the attempt to create a current is blocked by the EMF. And over time, the current is established. Now, you can try and manipulate what's happening here. You can put something like a variable resistor. I've not used this symbol very much, so the one I'm going to choose to use is this, a variable resistor. In a variable resistor, I could choose to increase or decrease the resistance of the circuit. So let's start by suggesting that I'm going to decrease the resistance of the circuit. If I attempt to decrease the resistance of the circuit, what will happen to the current passing through the circuit? There's going to be an attempt for the current to increase. So in this setup, the current's going to try and increase in the circuit. Now, an increase in current will attempt to create an increase in magnetic field. Inductance tends to prevent that, or tries to prevent that, which means that during the time that I try to increase the resistance, a back EMF will be created to try and prevent the increase in current. And the back EMF will be in this direction to oppose the change in the current. Now, the reverse of this also happens. If I take my resistor here and I try and increase the resistance, what will that do to the current? It will decrease the current, or try to. So that will make the current go down. That's going to attempt to drop the magnetic field. Under this circumstance, I will get a new EMF, but this EMF is going to attempt to be in the same direction as the current that's already there. It's trying to prevent the circuit from losing current. Now, I described all three of these scenarios with the whole intention of trying to give you an idea of what the usefulness of an inductor is. An inductor attempts to stabilize the current. An inductor attempts to stabilize current. It tries to make the current stay the same value. Now, it might not be obvious, but capacitor circuits try to stabilize voltage. They try to maintain the same voltage. Inductor circuits try to maintain a constant current. Now, if you can't see the usefulness of this, somebody already asked on Friday, is this how you make, like a surge protector? And this is exactly how you make a surge protector. And that's the first thing that's in your surge protector. You break it open and you'll find an inductor inside there. Usually, if there's a nice one, there'll be a small transformer in there and an inductor and a capacitor. A good surge protector tries to maintain both voltage and current so that if there's a surge in the line or a drop in the line, it maintains it. Now, this doesn't come out of nowhere. This whole thing, remember, is still predicated on conservation of energy. So if you try to drop the current, it will make up for that current by losing some magnetic field to maintain the current that's there. That energy comes from the field in the same way that the voltage in a capacitor comes from the electric field inside the capacitor. So if you try to take away voltage, the capacitor will try and reestablish it. This is why when we switched off our circuit that had a capacitor in it, the bulb didn't just go out. It faded out. Same idea. When we first flipped on the voltage of our capacitor circuit, the bulb, didn't come on for a while. It took some time. It came on right away and then slowly faded out as the voltage got established in the capacitor. An inductor is going to behave in the opposite way of a capacitor, though. And there's two ways to kind of think about it. But the first way I want you to realize is just the obvious, that T equals 0 and the closing of this switch. I want to remind you, we're trying to establish something. In an inductor circuit, at T equals 0, the voltage across the EMF across the inductor is maximum. And the current in the circuit is 0. At time 0, when you first close the circuit, boy, they're really mad at that door. I hope they showed that door a lesson, taught it, not to swing that way. Now, you need to contrast that with the capacitor. Capacitor did the opposite. In a capacitor circuit at T equals 0, the voltage across the capacitor was 0, current was at a maximum. In an inductor circuit, it's the opposite. When you first close the circuit, time equals 0, the voltage across the inductor is a maximum, but it's in the opposite direction to try and prevent the establishment of current. Current in the circuit will be 0. Yes, sir?
Is the EMF you're talking about in this case, is that the back EMF?
This is the EMF across the inductor. And yes, it's maximum, but it's, I guess, if you'd like, negative. It's in the opposite direction of the applied EMF, this one, which will say EMF of the battery. Is that okay?
Yeah.
All right. So let's put the math to this for just a minute. We're going to define inductance based on this property. We'll use a capital L for inductance. Sorry, guys who are also in mechanics. You're learning about angular momentum, which is also capital L. You got to keep it all straight in your head, right? So good luck with that. I try to do my best too, but capital L is a symbol that we use for inductor. And it's proportional to the rate at which the current changes. And there's an explicit negative sign to remind us that it's in the opposite direction of the rate that the current is changing. I mean, truthfully, I should put that negative sign in here to kind of indicate that it's about the direction that the current is changing. So if the current is trying to increase, the inductance is in one way. If the current is trying to decrease, the inductance is in the other. This is very similar to this relationship that we used for capacitance. So we use the EMF symbol more frequently now. If I wanted to make these look the same, then I would do that. This is, remember, the voltage across the inductor. So if we're going to have a lesson where we're going to use, Kirchhoff's laws to try and figure out how our circuit behaves, this is what we will substitute in for the voltage across an inductor. Now, don't be too worried about this, but don't throw it away either. If you remember, in a voltage across a resistor, it's equivalent to IR. We use that to create a differential equation for capacitors. We subbed in dq dt for I. In an RL circuit, which we're going to be getting to pretty soon, we have a very explicit differential already. We won't have to be subbing something in to get an extra point. So you're not going to get an extra point for that on the AP exam either. This is the definition of inductance. If you want, it could be defined the same way we define capacitance. Capacitance was defined by the charge per volt that it defined. So if we want to do the same thing for inductance, it's the voltage per rate of change of current. It's just that looks a lot harder on the eyes. I don't know why I put an equal sign on this side. These are just similar relationships. This is how you define capacitance. This is how you define inductance. In fact, inductance being defined as the voltage across the inductor divided by the rate of change of the current, with a negative sign in there to remind us it's in the opposite direction. This is a volt per amp second. It's pretty ugly. That's a volt second over amp. Oh, that's just hideous, isn't it? Keep going with this. Remember what a volt is? A volt is a joule per coulomb second per amp. What's an amp? Coulomb per second. That makes this a joule second squared per coulomb squared. Of course, a joule is a Newton meter second squared per coulomb squared. A Newton is a kilogram meter per second squared. The seconds cancel here. And that's not a surprise. It might be a surprise to you guys, but I would expect something about time to go away because this is an object. An inductor is something that can store energy. It's not time variant. We'd find the same thing with a capacitor. There'd be no issue about time in its unit. And so we get something without time in it. I would probably know this one. It's the most applicable. And worse yet, all this is for naught because we actually have a name for this called the Henry. So just like the capacitance, we had one for that called the farad, we have a measure for the inductor called the Henry. I have no idea who Henry was. I don't know if it's her first or last name. Don't care. And you don't have to show me how smart you are because you can work Wikipedia or ChatGPT. I don't care. I haven't learned it this far in life who he is or why he's important, and I'm not about to start now. So if it's important to you, look it up. But we do call it the Henry. And the Henry is unit of inductance. And I'll use it in the same way that we use the farad. Notice it's based on the amp. So a 1 Henry device is big. The ones I bought were 3 Henrys. They weigh about a quarter pound. They're just much bigger than I intended them to be. And we can't, like I said, it's hard to use them in our circuits. Okay, this part's going to be because I want you to have all of the knowledge. Do you remember how we used to figure out how to express capacitance for different shapes? So, for example, a parallel plate capacitor was the area of the plates times epsilon naught divided by the separation distance of the plates. You guys remember that? And then we did it for different types of shapes. So we did a spherical capacitor and a cylindrical capacitor. Do you remember that whole process for figuring out how to get the capacitance of a circuit, which usually started figuring out what electric field was produced by the charge that was placed on the plates? We're going to skip all that for inductors, mostly because it's not really done, but also because making a magnetic field, as we've seen, it's hard to get a uniform, straightforward to understand magnetic field. They tend to be kind of a mess unless you have a very collimated set of coils or you have a very easy to understand geometry. With capacitors, we can only look at 3 different geometry as it was. For inductors, it's just going to be one. It's just going to be a coil of wire. But I would be remiss if I didn't at least talk to you about how we figure out what the inductance is of a system. The first thing to remind you is that inductance is based on back EMF, and back EMF is based strictly on Faraday's law. So if we start with the idea that the back EMF is created because the flux is changing, then we can immediately use Faraday's law as our expression for the EMF produced in this fashion. So if I drop that in, I'm putting Faraday's law in for the EMF across an inductor. I guess I put my negative sign there. The first thing I point out is that the negative signs cancel. Faraday's law already had a negative sign to indicate the direction of the magnetic field that was required to produce that EMF. In the same way that the back EMF is in the opposite direction of the rate of change of the current. So those negative signs immediately go away. Do you notice that both of these are derivatives with respect to time? Both of these derivatives are made with respect to time. If you can take the derivative with respect to time of both sides of an equation, you can remove it from both sides of an equation. So we can write this as N flux equals L current. Now, if we solve this for inductance, we find the principal things necessary to increase the inductance of your device. And there's no surprise here. Number of coils is going to make a difference, right? How much current you can pass through the device is going to make a difference. And how much flux you can get out of your device is going to make a difference. So, again, we have a similar relationship to the way in which we create capacitance. It's about charge and voltage. Here it's about flux and current. So it shouldn't be a surprise, but an inductor side is going to be similar in how you can ramp up how much flux you have per your applied current. A system that gives you more flux for your current will have more inductance. And that's what I want you to take away here, is that we want to use something where we have a lot of flux for our current. Look at the different ways that we've talked about flux. A solenoid fits the bill the best. And so we tend to use solenoids here. They give you the most flux for your current. Every other device tends to have less magnetic field. So every inductor basically is a simple solenoid because it's the way you get the most magnetic field for your buck. Just gonna. All right. So the point of today, the whole real thing I wanted to talk about was, all right, what are these going to look like in practice? And this is what you actually have to be able to figure out. We need to come up with the charging profile of an inductor circuit. And, of course, eventually the discharging profile, which poses its own problem. So we're going to start with the talk about an inductor circuit, an RL circuit. So switch 1 here, resistor here, inductor here. You can, if you wish, assume that the inductor in this circuit has its own internal resistance, and that is R, or you can assume the inductor has zero resistance and the resistor is something else that's added to the circuit. But as I said at the beginning of this, all inductors are going to have some amount of internal resistance, and it may incredibly impact your circuit. So I just tried to use a simple inductor with the bulbs that we have. The bulbs are 3 ohms. The bulbs won't light up with this inductor. No matter how long you wait, the inductors have 100 ohms of resistance, which means the 6-volt batteries, they're barely pulling hardly any current. There's not enough current even to measure with our meters, the ones that still work. So as inductor circuits go, the trade-off between inductance and resistance can play a significant role in whether your circuit can behave in the way we're going to describe. However, you still need to know how it behaves. And you're going to have to be able to generate the differential equation and solve the differential equation to come up with the charging function and the discharging function of an inductor. So we start with Kirchhoff's laws to come up with the charging equation for an inductor. A single loop circuit, assuming that at t equals 0, current equals 0. So close the switch at t equals 0, the current in the circuit is 0. Let's begin there. That means that in our circuit, Kirchhoff's laws indicate that there will be voltage drops across my circuit. Not a surprise. Don't let this part be a surprise. There is an explicit negative sign in the function for the EMF across an inductor. Because it's not a drop, it's an active circuit. It's trying to prevent the flow of current. Its potential will be in the same direction as the potential of the applied battery under this circumstance. So you have to put in negative L di dt when you replace the EMF for your inductor. And the negative sign needs to be there. Of course, the resistor is still going to be IR. So in this circuit, it's already a differential equation without you having to do any substitution besides putting in the definition of an inductor. So we don't get any points here from reminding ourselves that I equals dq dt like we did for the capacitor circuit. So if it says, using Kirchhoff's laws, derive a differential equation that could be used to determine the current in the circuit, your differential equation is this.